Hey everyone, welcome back to mini lecture number 10 for Computer Science 252 at the University of Wisconsin-Eau Claire. In this lecture, I will be talking about sockets. I really encourage you to look at one or either of these two links down below. Consider them your required reading for this section. So to begin, I'd like you to review what is TCP/IP, what is an internet protocol, and why is it important for network communications. If you feel comfortable with those, then feel free to move on. But otherwise, take a sec to think about this and see if you can come up with some answers. What is a socket? A socket is one end of a communication pipeline. So in order to be able to communicate from a host to a server or a client to a server or a server to a client, we need to establish sockets, on both ends. You can think about a socket as being a telephone if you're trying to talk to somebody, across the country. Each of you need a telephone. That telephone is going to be unique to you, but it's going to connect you to, it's going to be like the medium through which you talk to your friend on the other side of the country. To build a server socket, these are the steps that you'll need to do. First, you'll need to create a socket to listen on. This is going to be a separate socket from the one that you transfer data on. In this socket, you're just listening to say, hey, is there a client that wants to connect with me? There is? Okay, cool. Get in line. Is there another socket? Oh, there is? Get in line. And so you build a queue of other clients or potential connections, and that's all that this socket does. It's like an operator in a sense. Now, it's not going to work just by itself if you created the socket. You need to bind the socket. And binding the socket means that you're going to connect the socket to your current host, and you're going to basically make it be ready for the world. Now, binding isn't enough. That's basically saying, let's do the prep work for the socket. You need to then say, okay, now turn it on. Listen for connections. Binding is like plugging in a phone. Listening for connections is like turning the power of your phone on, if it's one of those old-fashioned phones. Once you've done that, you can then begin accepting connections. Now, when you accept a connection, this is basically what you'll do for each of the connections that you might accept, and you might have more than one. You might put this in a loop. First, you have to accept a connection request, and when you do this, you'll create a new socket with a client. So you'll have a socket for listening on, and you'll have a socket with this client. Two separate sockets. One is listening to anybody who might want to connect to you, and then you'll have a special socket just with this client. And you might have other sockets for other clients. One for listening always, that's your server socket, and then another server socket for each client that you're talking with, that you've actually accepted a connection with. Then on that socket that you're talking with that client on, you can send and receive data. You don't want to send and receive data on the listening socket. That's like sending and receiving data with an operator. Operator's not interested in your data when you're talking on the phone. You want to send and receive data to your friend, therefore you use the connection with your friend's socket. So that's the socket that you want to use. Then you close the socket with the client. Once you're done sending and receiving data, close the socket with them. Your business with that client is done. Maybe they'll call back another time, but for now, that's it. Once you've done that, and you've done this for all the connections that you want to make, then you can close the listening socket, and that's the end of the server. To build a client socket, it's a lot simpler. You first create a socket, so you allocate space and memory and settings and stuff for the socket. Then you connect the socket to the server by asking, hey, can I talk to you? And the server's like, yeah, sure, or maybe not. But hopefully they're like, yeah, sure. Then, if so, then you'll get a socket ID through which you can communicate with the server. You can send and receive data, repeating as necessary. And then when you're done talking to that server, then you can close the socket. And that's it. Let's see how to do this. Header files for sockets, there's a bunch of them. Sometimes they can be more complicated, sometimes they can be less, depending on how many details and how much fine-tuned control you want. But these are the socket headers, or the headers that are related to using sockets for TCP IP in C. Some of them you may need more of, again, for other ones you might not need as much. And there's some of the functions and data types and stuff that are related to them. Now when you create a socket, this is how you would do it. First, you want to say there's a function called int socket, and this is going to ask to create a socket using some protocol family. Now this is a constant that you can pass it, int type and int protocol. The protocol family is basically like, say, AFnet. It's an address family. The type, you can say what kind of socket do I want. Do I want to send it as a stream, which is like a byte stream, just like your files that we're used to? Or do I want to send it as datagrams? TCP/IP usually doesn't use datagrams as much. It's a little bit more deprecated. Usually it uses stream, but you can use datagrams if you want to. It supports it. The protocol can be different constants here. We're going to use TCP/IP, but you could also do UDP if you wanted to. And this will determine different settings and different protocols and different ways of talking. And this will return a non-negative value for success. That's the file descriptor for the socket, or -1, meaning failure. This didn't work. Try again, maybe, with different settings. Here's some example code of creating a socket. So int socket fd file descriptor equals socket AF inet. So it's an internet address socket stream. So we're going to make it the socket use streaming data as opposed to datagrams. And then we're going to use TCP/IP or TCP rather than UDP. So then check if socket fd is less than 0. Say it failed. Maybe quit. Maybe do something else. Otherwise, you can use it. To destroy that socket that you just worked so hard to build, you use just a simple command that takes a single action, a single argument, int socket. This will tell the underlying protocol stack to initiate actions to shut down communications and deallocate resources associated with the socket. Basically, remember how we have a bunch of different layers on the web stack? It's going to talk to those different layers and say, okay, shut down, shut down, shut down, until everything that we need to shut down is shut down associated with the socket. 0 in success, -1 on failure, the usual. How do we specify an address? We have to pass it something called a sock address structure, a socket address structure. So it's defined something like this. So struct sock address, there's an unsigned short. This is what kind of address family that you're dealing with. And then also you want to pass it some information about that, the family specific address. For TCP/IP socket addresses, you can use the specific type of structure, socket address in structure, for instance. This uses 32-bit internet addresses, 16-bit port number. That's just how they work. Just see examples of how this is done and copy and paste. If you're really interested in how this, you can look into more information to customize this. But other than that, I'd suggest you just follow examples that you see online. So here is an example. So struct in address, unsigned long s address. So this would be like the internet address, 32-bit address, unsigned long. So that's basically like, your IP address, if you will. Then we're creating a struct socket address in, and so then we're saying what's the internet protocol. We might set that value equal to AF inet. Unsigned short SYN port. Socket in port, it's the address port. Struct in address s in address, it's the internet address, like the IP address. And then there's character array, but we are not going to use that. And that's it for now. And to do this, to use this, what we typically need to do is fill in some of these socket address in fields, cast this struct to a socket address struct instead, and pass that into socket functions that will use it. Again, I would suggest that you see tutorials online for all the messy details of how to do that. Suppose I have 32 ones and zeros, and I send those 32 ones and zeros, my integer, to another computer for a series of ones and zeros. It turns out that those ones and zeros can actually be interpreted differently for different computers, depending on what endian they have. So for instance, some computers will use big endian. So they'll store numbers with the big N first. That's just how they do it. Other computers will store them with the little endian first. And that's just how they do it. So if you've got this hex number B34F, they may reverse the order of them. This doesn't really matter for most of our details and for binary representations, but if you're going to be sending these kinds of things over the internet to other computers, you might want to know what's going on. There's also something called host byte order, and that may be a little bit different depending on what computer you're using, what your host is. So how do you know which of these different byte orders to use? Well, there's different converters that are provided. So there's host format, which is your local computer here, and there's network format, which is a generic format, whatever is being sent over the internet. So if you want to convert your short or long to the network version, you can use host to, so H host to meaning convert to, N means network. So H2N means host to network, short, long, long, short. That's the abbreviation, the etymology. So basically it's converting your number, your series of ones and zeros to the ones and zeros that will be sent over the web and vice versa. So if you get some stuff over the web, maybe you want to convert that to the kind of endian style that your computer uses, just to be safe. If they're the same, then calling this function won't do anything, but if they're not the same, it'll make sure that it's put in the right way. So convert to network byte order before sending. And if you are receiving data, make sure that you convert to host byte order, in other words, convert to your local computer's byte order when receiving. A TCP server is going to perform these 4 steps. As we said before, it creates a TCP socket using the socket call. It assigns a port number to the socket using bind. Now it's telling the computer, okay, I've created a socket that I hope to use for connections. Now please open this port so that I can do that. And then it will start actually listening to it, plugging in the phone and talking to the operator. Then it will repeatedly accept new connections, send and receive data using those or write and read, and then it will close the client connection using the close function. That's our review, but let's now look at this in more detail. When we call the listen command, what's happening under the hood? First, it's telling the computer to, telling the underlying TCP protocol to listen for connections from clients, which kind of makes sense. It's going to change the state of the socket actually. So when we call int listen, we pass it a socket, our listening socket, the server socket, and we pass it this queue limit. The socket, the first argument, is a socket descriptor from creating the socket when we first called the socket command. The queue limit says, okay, so I want to listen to, I'm only going to be, okay, so basically there's going to be a bunch of clients that might try to connect to you. And maybe you'll listen to them all at once, or maybe you'll have a line. So if you have a line, what is the length of that line limit? So for instance, if I put 5 for the queue limit, that means that the operator will have a list of 5 people in line, like a wait list. And if there are more people than that, then they'll just get a connection refused, saying, nope, the server's busy. The server has too many connections right now. So, remember, a bound and listening socket does not yet receive does not send or receive data. It is just there to listen to potential connections and to put them in line. Then there'll be another socket that you can open to actually accept those connections. But a bound and listening socket doesn't send or receive data. Also, the server will create new sockets, one for each client connection, and it will send and receive data on those sockets, not on the listening socket. The server will actually get a socket to send and receive data to from each individual incoming client connection that's waiting in line on the other socket, this listening and bound socket, by calling accept, and it will just take whatever client request is next in line on the bound and listening socket in that line, in the queue, and it will basically say, okay, let's take that next one, let's open it for a connection, and let's talk. What happens then when we call accept? First, it takes the next connection from the queue of the listening and bound socket. If the queue is empty, it will block. In other words, it's going to stop, and this function is not going to return until a connection request arrives. So there are unblocking versions of this where it just says accept the server, and if there's no server in line, just keep going. But this is a blocking call by default, accept is, that is. So if you call accept and there's nobody in line, it'll just wait until somebody does get in line. When somebody is in line, or when somebody does connect, it returns a file descriptor for a new socket. This is the socket that you want to send and receive data on. And it will return -1 on failure. Here's the command that you can use. So int accept socket is the socket descriptor to the originally created socket. So that's the socket that you're listening on, the bound and listening server, or the bound and listening socket from the server. And then you're passing it this struct socket address, a pointer to this structure, which is going to contain some information about the client on return. So this function is going to fill in that struct. And then unsigned int address length, that is going to, it's a pointer to unsigned int. So it's going to say, here's the maximum size of the client address structure. Now what does the client do? The client, of course, their job is to initiate communication with the server. They're going to call the server and say, hey, let's talk. The 4 basic steps, again, are to create a TCP socket, to establish a connection to the server, to communicate with the server by sending data or receiving data, and finally, to close their connection with the server. And that's mostly on their end. So on the client's end, the create socket command is going to be pretty similar to what you did with the server. You're saying here's all the same variables that we had before when we're creating a server socket, same ones here. So when you connect, the TCP socket must be connected to another socket before we send or receive any data. So you have to, the client will initiate the connection, the server is going to wait for the client to connect, and then finally, it'll actually have a connection when the server says, okay, yeah, I accept your connection. But in the meantime, when the client is waiting to connect, the client's just basically saying, hey, can I have a connection with you? And it will just wait and wait and wait and wait. So the client is going to do that using the connect function. The connect function looks like this. The first argument socket is the file descriptor of the socket from when you created that socket on the client side. Foreign address is a pointer to a struct socket address. This is going to be a socket address that contains the internet address and port of the server. So this is basically who you're trying to connect to. Finally, address length is the length of the address structure, the size of the struct. So this is a request to connect with a particular server specified by foreign address. When you send information through a socket, you would use this command, send. Or this is one of commands that you could use. You could do other ones as well. So what do those commands mean? Int fd or sock fd is the socket through which you're sending information to the server. You could be talking to multiple servers, perhaps. So you might have multiple sockets open. The void star message. Void star is a way in C+ or in C to refer to a. It's a pointer to void, meaning type unknown, basically. It's not that it doesn't have a type, it's just that we don't care about the type yet, or the type doesn't matter. So for instance, when you allocate stuff using, say, malloc, it returns a pointer to a block of memory, a certain number of bytes of memory that you specify. And so the return type of malloc is void star because it doesn't care what you use that memory for. You could have allocated it for a struct, you could have allocated it for an array of integers, you could have allocated it for an array of doubles, or you could have just allocated it for one double. So the type doesn't matter, and that's why we have to cast whatever we had before, whatever the return value is of malloc, into, say, a double star, or an int star, or a char star. So that's what's happening here, but in reverse. Now we might have like a message, of text, a string to send, and we might have a character array of 200 characters, and the string itself is only, say, 20 of those characters, plus a null, so 21 characters that we want to send. So this is going to point to the first address of that buffer that you're going to send, your box size, if you will. Int is going to be the length of the data. So if you're sending 21 bytes of data for the C string, then you might want to say only int length equals 21, even though the box size might actually be a little bit bigger. Flags are just some extra settings. You can check more information about that. Now when you receive data from the server, you would use this function, or one of a couple functions, but this is the most common. So here, buffer is the box that you're reading into. So the server might be trying to send you a lot of information, maybe just a little bit of information, but you're saying here's the box that you can put the information into, and here's the length or the size of that box. Here's how many bytes that box can fill. Notice that the type of buff is void star. That again is saying I don't know the type of this. It could be giving me a bunch of characters. It could be giving me a bunch of doubles. It could be giving me a bunch of bit sets. I mean, it could be any kind of data, but it's giving me this many, up to this many bytes. So the reason that you're passing in the maximum length of the buffer is, say the server wants to send you a string, hello world. You allocate a box size of 200 characters. So that could have a C string of 199 characters plus a closing a null character at the very end for 200 characters. So you would allocate using maybe malloc that character array of size 200 characters, size of 200 times size of character, which is 200 bytes, and that would be your length, 200. But then the server might have actually tried to send you 250, and so the server might get some kind of result saying, hey, I was only able to send 200. And the server would have to deal with that. But you at least will be able to receive 200. That's what you've allocated here. So buff is your box size, if you will, and int is the size of that box. Sorry, buff is the box, length is the size of the box. Then you would have to take whatever you got in buffer and cast it to whatever other kind of type that you want, like maybe a double star for an array of doubles, maybe a char star for a C string, and so on. There's other ways to do I/O besides send and receive. So for instance, if you want to do binary input and output to a file descriptor, you can use the read and write commands. And this will do, like if you wanted to do, say, text-based ASCII input and output of an array or other data to a file, you'd use fprintf, for instance, file printf formatted. So printf is print formatted, fprintf to a file print formatted. But if you wanted to write binary, you would use write and read. And the first argument would be the file descriptor. Here we're reinterpreting that to be the socket file descriptor because, hey, a socket is a file descriptor. It's just an integer referring to a file descriptor that this process has. Then const void message is the data. Again, we don't know the type, so it's void star, but it's the buffer containing all the data that we want to send to this socket, and length is the length of it. So this is another way of doing that. Instead of doing send and receive, you can just use read and write and treat it like file input and output. Data encoding. Let's assume that we're working for a bank, and we're creating a server and client, and we send two numbers to another application, the total amount of money deposited, the total amount of money withdrawn, and we're assuming that the unit is the penny. So the numbers are going to be integers as opposed to doubles or floats, so we don't have to worry about the problems caused by, or described in, like, say, the Office Space movie, right? Where they skim off, rounding errors and stuff. Both the sender and the receiver must know how the numbers are represented. Are they in US dollars? Are they in yen? Are they in won? Are they in some other currency? So what you might do is what you need to do is you need to have a way to construct messages. So here you have a struct int deposit, int withdrawal, message struct. And message struct dep deposit, you first would take host to network long. So you'd take the deposits, some other variable named deposit. This is actually how many deposits that the customer wants to deposit to the server. And you would convert that into, from your host value of deposits, whatever the user, the user or client did, you'd first want to convert that into the network version of a long and store that into message struct dependence. That takes care of endianness. And then you do the same thing with withdrawals. You convert from a regular integer to whatever network style or whatever endianness the network wants using h2nl. And then finally, once you've taken that, you've packed your struct, if you will, and now you can send that struct, send the address of that struct, send the size of the struct in bytes to the server. It's a server socket S. Something else you might encounter is alignment and padding. Now, not all machines will represent a message as the same number of bytes, which is kind of crazy. Some compilers will align the fields of structures to word boundaries based on type, and some won't. So if you're working with a protocol, this protocol has to take that into account. So here's an example. So if we're using that bank account analogy from earlier, suppose you have a struct with the number of cents deposited, an unsigned short number of deposits, the number of cents withdrawn, and the number of withdrawals. So that's what you want to send from your bank client to the headquarters bank's server. So you're working at a branch office, and that's where the client is, and the client wants to send the server a message, here's the deposit, deal with it. And then the server's like, okay, cool, I'll store that into my master database of bank accounts at my bank. So you would you say, okay, cents deposited, message buff.cents deposited equals whatever. You fill out all those little blanks. Cents deposited is an integer, so it's 4. Number of deposits unsigned short is 2. Integer 4, and then unsigned short with number of withdrawals is 2. So right there, we're looking at 12 bytes. So you send S, send the address of the message buffer, that struct, and you send the size of message buffer. Okay, cool, you do that. So size of message buffer, 12 bytes. But on some machines, this will be a 14-byte message. What the heck? How does that happen? What happens is the compiler will say, hey, there's an int, there's an unsigned int short, there's an int, there's an unsigned short. Now, it's going to try to align this to a word, which on most computers is 4 bytes. That's like the size of the processor, or maybe 8 bytes. So what will then happen is it will, an int will be 4 bytes, so that's a full word. Unsigned short is not a full word. So instead of that being just 2 bytes, it will actually take up 4 bytes in memory. There'll be 2 bytes for the unsigned short, and then there will be 2 blank bytes that are just making it so that it's a multiple of 4 bytes, the word size of that processor. And then unsigned short number of withdrawals at the end will just be 2 bytes, and a lot of times the processor will treat that as 4 bytes under the hood, but here we don't need to do that because it's at the end of this thing, so it will just truncate that and make it 2 bytes. So yeah, we just got an extra 2 bytes. How the heck do we deal with that? Well, you need to worry about the alignment and the parsing, and there's ways to do that. Won't cover that here, but I just want you to be aware of that. Not all fields will have the size of the message known in advance, but if all fields have a fixed size and the size of the message is known in advance, then we receive the expected number of bytes, which is great. But if that's not the case, then we need to have a delimiter and parse as you receive. So for instance, you might say, okay, the first field is going to be a string, and then have like a comma, and then another string, and then a comma, and then another string, and that will all fit inside one big message. So that's something that you might need to think about too. If that's the case, then you're going to need to have the server and client both understand what that protocol is, and they're going to need to parse that, to package up a message into these delimiters, and then to be able to read that. Oh, complicated, but it's cool. So here are some review questions that I encourage you to think about. If you have any questions, let me know. So I would encourage you then for practice to, you've done lab 10 or are working on it now, I'd encourage you to look at each of the routines in that library and make sure you understand each part of them so that you could write your own little mini server and mini client from scratch without calling the pre-built routines in the UWC sockets library. Then try one of the extensions to that lab. Try sending a struct instead of just an integer. I've shown you a little bit about how you can do that here, but look into it and see if you can do that. That's all for now, so thank you for your time and attention. I'll talk to you later. Jess out.